Today's networks have a mixture of applications and workloads, all with different consistency requirements. Some applications require predictable latency, while others sustain throughput. It's usually the case that the slowest flow is the ultimate determining factor affecting end-to-end application performance. So to try to satisfy all these varied conditions and achieve predictable application performance, we must focus on consistent bandwidth and unified latency for all flow types and workloads. Poor performance is due to a lot of factors that can be controlled or not. One factor that can be monitored is the buffer sizes in the network devices that are used to interconnect source and destination endpoints. Poor buffers cause bandwidth to be unfairly allocated among different types of flows. If some flows do not receive adequate bandwidth, they will exhibit long tails and long completion times, degrading application performance. Essentially, the speed of the network is all about how fast you can move and complete a data file from one location to another. Some factors you can influence and others you can't control. You can influence, for example, the physical distance from one location point to the next. This is why we see a lot of content distributed closer to the source and used with, for example, intelligent caching to improve user response latency and reduce the cost of data transmission. The TCP connection-oriented procedures will affect application performance for further distant endpoints than it would for source and destination pairs internal to the network. We can't change the laws of physics and distance will always be a factor, but there are ways to optimize networking devices to improve application performance. One way is to optimize the buffer sizes and select the right buffer architecture to support applications that, for example, send bursty traffic. There is a big debate as to whether big and small buffers are best, or whether we need to use lossless transport or simply drop packets. How long it takes a flow to complete is significantly affected by the TCP congestion control procedure and the network device buffer. TCP was invented over 35 years ago, and its job is to make sure that sent blocks of data are received intact. It does this by creating a logical connection between source and destination pairs, with the finding of endpoints carried out at the lower IP layer. The congestion control element was actually added later to ensure that data transfers can be accelerated or slowed down based on current network conditions.